Welcome to another video as part of the Pavilion video series. SQL Server Workload Distribution, part 1 of 3. Storage latency inside a SQL Server. So after you've tuned everything else, including adding fast storage like Pavilion, how do you tackle SQL Server when the SQL Server engine itself becomes the business bottleneck? I'm Kostas Apopoulos, the Chief Field Technology Officer for Pavilion Data. I'll be joined by our SQL Server expert and consultant, David Klee, the founder of HeraFlex Technologies. So in this video, remember I said we're going to focus on, after you've tuned everything else, including added fast storage like Pavilion, how do you tackle that SQL Server storage engine when it becomes the bottleneck? So in that, we're going to talk about the database file structure, storage latency perspectives, the database storage engine itself, disk stall, and workload distribution, including a couple demos. So before we get into the presentation and an introduction of David, let's talk about Pavilion and how Pavilion unleashes the power of Windows and SQL Server. Of course, we work well for every single workload, but if you have super high bandwidth per host needs with ultra low latency, this is where we really shine. Whether that's large or small block sizes, whether that's read or write. Specifically, that relates to SQL Server. So that Pavilion platform that has impressive IOPS and the millions of IOPS and the impressive throughput, but what is most impressive is that latency in the range of 100 microsecond read to 25 microsecond write latency. All of that packed into 4 rack units and over 2 petabytes of usable capacity. Whether you're leveraging that platform for a Windows environment running SQL Server on bare metal, leveraging NVMe-TCP or NVMe-RoCE, we have certified drivers from Windows to support both of those environments. What's really impressive, you can get similar or same performance of bare metal inside of VMware running SQL Server in Windows, leveraging VMware 7.0 and Pavilion support for NVMe-over-Fabrics RoCE for VMware 7.0. So whether it's bare metal on Windows for Windows or whether it's virtualized inside of VMware, incredible performance, but ultimately low latency, which drives incredible results for SQL Server. So our presenter today, I'm excited to introduce the founder of HeraFlex Technologies and Sequilibrium Education, David Klee. David is an incredible performance tuner, enterprise DBA, and infrastructure architect, and self-proclaimed geek. David's expertise in SQL Server and VMware are the best I've seen. His ability to intersect the storage, the software, and the virtualized infrastructure or non-virtual infrastructure, and to tune the system to get the most out of SQL Server is incredibly impressive. So with that, I'll turn it over to you, David, and let's learn more about SQL Server.
Okay, thank you, Costa. Let's take a look at our database file structure. So first of all, there's this thing out there called the instance, and this is quite literally your SQL Server installation. It's got its own storage engine in it. It's really complicated. It's got its own operating system in it, actually. Then we have one or more databases. Now, the databases are made up of these things called logical file groups. It's essentially a container, a logical placeholder to have one or more database data files in there. The primary data file is always called an MDF. The secondary data files, and you can have a bunch of these, are called NDFs. Now then there's a transaction log file, or LDF. This is not a traditional log file. It's essentially a ledger of every change that you're making inside this database goes there first. So you make a command to create, update, insert data. It gets hardened into the transaction log, and then it gets sent to the file group, which then will distribute it across the individual data files in the file group. Now, zoom out a little bit in the environment. So now we've got an operating system, be it Windows or Linux. We've got multiple Windows or Linux-based formatted drives. Then virtualization may be in there. We'll talk more about that in a different video. And then you've got the underlying storage itself. There's a lot of layers of components in here. What if the storage underneath is not the primary bottleneck to performance like it has been in, for decades now? What if the virtualization layer or your interconnects are tuned properly as well? This would actually make a lot of sense. What happens when a DBA gets a long I/O alert in the middle of the night when backups are running or index maintenance are running? It's literally a warning of, let's say, 15 seconds or longer that this storage command took to take place from the database storage engine's perspective. And then you go look at the storage device and we're like, yeah, we're 200 microseconds. You know, what gives? This telemetry doesn't line up. There's a lot of stuff in here, and these are real numbers. You know, we're looking at 0.8 millisecond read on a SAN line, and the database engine can be reporting something entirely different and way too high. Now, one of the big challenges is if the underlying storage and all of these associated queues are really cleaned up, you can end up with congestion inside the database engine itself. And this gets really challenging because your telemetry is saying everything is bad, you know, from a database perspective. And then you go look at the SAN and the hypervisor and everything's fine. And what the heck is going on? Well, SQL Server measures its own perspective on storage latency and it calls it disk stall. It's kind of interesting. It's quite literally a measurement of the amount of milliseconds held up accessing a data file. The hard part here is that it's really complicated. There's a lot of pieces in there. And when you have a lot of highly concurrent workloads, it can end up tripping on itself, essentially, causing metadata contention inside the database engine, and your disk stall rates will begin to climb and elevate. The problem here is that a lot of folks will take this as the objective source of the truth, and it's accurate from its point of view. But you have to overlay this with operating system level storage latency metrics. If there's a hypervisor involved, you have to go measure it there and look at the physical storage stats. And what you'll find is really interesting. As you clean a lot of these queues from the bottom to the top, if you go from the bottom to the top, you look good, 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 bad. Well, what's different in there? It's going to be access time within the database storage engine, and it's literally tripping on itself. So here's where things get more interesting. You can actually see this. It's a SQL Server DMV, sort of dynamic management view, and you can actually query this and actually see the built-in measurement that SQL Server maintains since the last time the instance turns on. And that's awesome. The problem with that is if you just query it at one time, it's a rolling average since the last time you turned this thing on. And that's not really accurate because you have things like backups and index maintenance and all this other stuff that runs around the day. And it can be very different depending on the time span that you're measuring this in. So if you go out to our website here, we actually have a script out there that can sample this data periodically, and usually, you know, every minute or two. And it stores it into a utility database, and then you can query it, and then you can compare that with the operating system level perfmon or IOStat metrics and a hypervisor layer and then the physical disk. And you can start to put them together and actually see very clearly where's our bottleneck actually at. So let's go take a really good look at this script and how to actually go set this up in your own environment.
We're going to create a placeholder database. So use any database you've got, DBA database, whatever. We're going to call this table a disk stall table. Server name, instance name, database ID and database name, physical file name, database file ID, average read stall in milliseconds, average write stall in milliseconds. The rest of this is also good information for you. Here's the secret sauce. This is a stored procedure that gives us the difference between the last sample and the current sample of disk stall. We're going to schedule this with the agent to run either once a minute or every 30 seconds or whatever frequency you want. And we've also got a proc in here to clean up after itself after so many days. Feel free to modify all of these. So now we're going to create a job in here to go schedule this. I like to do, honestly, every 30 seconds to a minute. You can see I've got just a normal DBA utility database in here. We're just going to execute the stored procedure that goes and gives us our diff. And then we'll go ahead and run this every 1 minute. We'll just run it around the clock, and that way we've got tons of good information. And then we'll go ahead and create the job that will clean up after itself. And again, use your best judgment on how long you want to keep the data around for. You may want to keep it around indefinitely in case major things change over time, or you may just want to keep it around for a month or two. It's completely up to you. In this case, we're going to execute this stored procedure that does the cleanup after 60 days. And I'm going to schedule it to run at a very specific odd time in the middle of the night that I know is not going to conflict with anything on this particular server. Okay, now this stored procedure has already had the opportunity to run, so let's take a look at the output, and we're going to see every database data and log file. The fun part is it has now calculated the diff between the last sample and the current sample. Disregard the very first sample because it didn't have anything to compare against. But you'll notice average read stall in milliseconds for both read and write. There's also a lot of really good info in here for number of reads, number of writes, number of bytes read from or written, which I find fascinating because now we can start to figure out the largest I/O consumers of any database in my entire environment.
Okay, so now we've got our disk stall rates. So we know, just by looking at the disk stall, we may actually have a hotspot on one of these data files. You could see high disk stall rates on a file. You could see high disk stall rates on a group of files in that file group if they're all being equally distributed. So step one, when in doubt, think about adding more files into that file group and rebalancing. We do have a how-to guide out here, hfxt.ch/mdf to ndf. We have a methodology for how to add more data files and tell this thing to load balance and spread all the data out. If you just add another data file in there, the database engine is going to try to round robin and go, well, we got an empty one and everybody else is pretty big, so we're just going to keep writing this new one. You may actually make it worse until that rate of data actually fills and meets everybody else, and then it'll start to load balance round robin. So let's take a good look at how to do this. Have you ever inherited a database that has a very large single database file or a set of single large database files? It's kind of a challenge. You end up with metadata contention, you end up with an I/O hotspot. It's not the most fun. So I have come up with a methodology for how to take that file and equally distribute it to more data files in the same group. Now, if you have control and ownership of the code, maybe you should consider adding more file groups, more data files for things like non-clustered indexes or tables that collide like customer data and then order data. You're commonly joining all of these things. If you don't, still consider adding more data files. This would be where you go and add more drives to the server, be it physical or virtual, more controllers, things like that. Here's what we do. If you go to my home blog with the link on the previous slide, you'll find this is how to scale out the MDF database files into more NDF data files. So let's take this database right here. It's pretty large. It's the HammerDB database that I've populated up to about 430 gigs, so it's a pretty good size. I generally don't like to see data files this big. So if you run this query right here, you'll find that we can actually look at the internal space rather than the total consumed space of this data file. And you'll find it's about 182 gigs, give or take. Let's say we want to add 7 more files to bring this up to 8 total. Take that value, divide it by the number of files that you want. And this is going to give you a very simple little integer here. Then that's going to be our target size. Glenn Berry is the source of that query. Go check out his diagnostic queries. Add more data files, whatever you would normally do, more controllers, things like that, so that we can better distribute this storage workload. So you can see here, I have the add database file command. So tpcc test 2 through 8. Now you'll notice I have set a max size. This value right here corresponds to this maximum megabytes ratio value here. You can do it through the GUI, you can do it through the script, whatever floats your boat. Now again, this is where you should really think, if you have control of this database, go in and add more file groups, maybe move non-clustered indexes over, or commonly join data, things like that. In this case, we're just going to assume that we don't have the control over that. Here's the secret sauce. We're going to run this little known command, dbcc shrink file, and we're going to specify the logical name of the primary MDF, and we're going to say empty the file. Now, I put a file cap on those new files. So it's going to run. And if you rerun this command over and over again, you'll actually see it load balancing and round robining between them. And it kind of pulses a little bit, and it's slow, but it's online, which is really, really cool. Now, when it gets to that destination size, this command will fail. I'm okay with this. It just says could not allocate enough space to let this thing continue to grow. At this point, if you look at the internal fill space, it's going to be almost identical. It'll be a little off just because of internal fill ratios and things like that. At this point, remove the max size from all these new files that you created and then go in and shrink that MDF file. Don't do it all the time, but a one-time operation is fine. Go shrink that file down to equal of the same size as the others. At this point, you now have an equally distributed database. So if you're not running the trace flag that automatically does this, as of 2016, there is a database scoped parameter here to auto-grow all files as part of the file group. Check this. This is the piece that will cause an outage. Not that big of a deal. Just schedule it for a maintenance window. You don't have to do it immediately. And at this point, you can turn around and you're going to notice that your I/O is going to be much better, more widely distributed. So if you notice, even little things like right here, this is a backup to null database backup command. What it does is it really is just performing a storage read test. But if you notice, in my lab, 941 megabytes a second without it. With this change, 2.2 gigabytes a second. That's a big deal. So now, when you run this, go resample your disk stall rates, and you're going to find that the metadata contention inside the database is going to drop considerably, and you should have a pretty good performance gain, and you're going to be better balanced with the underlying infrastructure. So take this, test it, validate. I hope you enjoy. At this point, you've now got the ability to go collect the telemetry and understand all of the storage contention possibilities at each of these layers. By the time you get done tuning all of this and spreading out the database workload appropriately, all the way into the database design, when you're looking at telemetry, it should be pretty darn close end to end. In all of my years of SQL Server engineering, storage latency matters more than anything else. This is where I see Pavilion fitting in. It scales, the NVMe media, the PCI switch architecture, the multiple active controllers, all of it matters. Costa's going to show some performance numbers that you really might not believe, but take it from me. I'm an independent consultant designing some of the largest systems in the world. Thank you. This thing works. I love the opportunity to share absolutely nerdy details about SQL Server data platforms. Back to you, Costa.
Thank you, David. Great insights as always. As we summarize this video, let's bring it back to something that's really core to SQL Server, latency. So as we look at a Pavilion storage array, it's always sub-microsecond latency, whether that's bare metal or VMware, whether that's read or that's write. Impressive latency drives lots of things upstream to SQL Server that are all good. It pushes the bottleneck from the storage to somewhere else inside a SQL Server ecosystem. So we have demonstrated through this table that is a disk speed on Windows with a single Windows host and a single NIC, some very impressive latency, whether that's Windows bare metal, the first two columns, Windows TCP and Windows RDMA, the read, and then the first two columns on the right. But what's equally impressive is the latency by taking that same ecosystem and put it inside of VMware. Similar or same latency, or in some cases better depending on the protocol than bare metal. So as we see, latency is key to SQL Server, and Pavilion can deliver impressive latency, bare metal or inside a virtualized VMware ecosystem. Thank you so much for spending time today with us, learning more about SQL Server and how to optimize the SQL Server ecosystem to get the most out of your investment. Special thanks to David Klee, our SQL Server extraordinaire. We appreciate all the partnership and all your insights you've given us today. If you want to learn more, come check out our other videos at www.pavilion.io or reach out to us via email at info@pavilion.io, or of course you can always call us on the phone. We'd love to talk to you about how Pavilion can help you optimize your SQL Server environment and get more out of your investment. Thank you for your time.